Direct path reads. This event occurs when Oracle instance query data from the data files asynchronously and puts this data into PGA instead of buffer cache in SGA. This type of event usually occurs during the use of temporary tablespace in the sorting operations, during the creation of lob segments, and when multiple sessions full table scan in parallel. The direct path read and direct path write wait events are related to operations that are performed in PGA like sorting, group by operation, hash join. In DSS type systems, or during heavy batch periods, waits on direct path read are quite normal. However, for an OLTP system these waits are significant. SQL statements with functions that require sorts, such as order by, group by, union, distinct, and rollup, write sort runs to the temporary tablespace when the input size is larger than the work area in the PGA. In order to solve this problem, the memory should be increased, parallel operations should not be done unless required, and pay attention to lob segments reads. Ensure the OS asynchronous I/O is configured correctly. Check for I/O heavy sessions/SQL and see if the amount of I/O can be reduced. Ensure no disks are I/O bound. Set your PGA_aggregate_target to appropriate value if the parameter work area_size_policy equals auto, or set *_area_size manually, like sort_area_size, and then you have to set work area_size_policy equals manual. Whenever possible use union all instead of union, and where applicable use hash join instead of sort merge and nested loops instead of hash join. Make sure the optimizer selects the right driving table. Check to see if the composite indexes columns can be rearranged to match the order by clause to avoid sort entirely. Also, consider automating the SQL work areas using PGA_aggregate_target in Oracle 9i database. Query the $sestat to identify sessions with high physical reads direct. Default size of hash_area_size is twice that of sort_area_size. Larger hash_area_size will influence optimizer to go for hash joins instead of nested loops. Hidden parameter db_file_direct_io_count can impact the direct path read performance. It sets the maximum I/O buffer size of direct read and write operations. Default is 1M in 9i. Direct path writes. These are waits that are associated with direct write operations that write data from users' PGAs to data files or temporary tablespaces. Direct load operations, for example, create table as select, CDAS, may use this. Parallel DML operations. Sort I/O, when a sort does not fit in memory. If the file indicates a temporary tablespace, check for unexpected disk sort operations. Ensure parameter disk_asinch_io is true. This is unlikely to reduce wait times from the wait event timings, but may reduce sessions elapsed times, as synchronous direct I/O is not accounted for in wait event timings. Ensure the OS asynchronous I/O is configured correctly. Ensure no disks are I/O bound. Read by other session. When a session waits on the read by other session event, it indicates a wait for another session to read the data from disk into the Oracle buffer cache. If this happens too often, the performance of the query or the entire database can suffer. Typically this is caused by contention for hot blocks or objects, so it is imperative to find out which data is being contended for. Once that is known, there are several alternative methods for solving the issue. When information is requested from the database, Oracle will first read the data from disk into the database buffer cache. If two or more sessions request the same information, the first session will read the data into the buffer cache while other sessions wait. In previous versions, this wait was classified under the buffer busy waits event. However, in Oracle 10.1 and higher, this wait time is now broken out into the read by other session wait event. Excessive waits for this event are typically due to several processes repeatedly reading the same blocks, e.g. many sessions scanning the same index or performing full table scans on the same table. Tuning this issue is a matter of finding and eliminating this contention. Latch-free waits. This wait indicates that the process is waiting for a latch that is currently busy, held by another process. When you see a latch-free wait event in the $session_wait view, it means the process failed to obtain the latch in the
Willing to wait mode after spin_spin_ count times and went to sleep. When processes compete heavily for latches, they will also consume more CPU resources because of spinning. The result is a higher response time. If the time spent waiting for latches is significant, then it is best to determine which latches are suffering from contention. A latch is a kind of low-level lock. Latches apply only to memory structures in the SGA. They do not apply to database objects. An Oracle SGA has many latches, and they exist to protect various memory structures from potential corruption by concurrent access. The time spent on latch waits is an effect, not a cause. The cause is that you are doing too many block gets, and block gets require cache buffer chain latching. Library cache latch. The library cache latches protect the cached SQL statements and objects definitions held in the library cache within the shared pool. The library cache latch must be acquired in order to add a new statement to the library cache. Application is making heavy use of literal SQL. Use of bind variables will reduce this latch considerably. Latch is to ensure that the application is reusing as much as possible SQL statement representation. Use bind variables whenever possible in the application. You can reduce the library cache latch hold time by properly setting the session_cached_cursors parameter. Consider increasing shared pool. Larger shared pools tend to have long free lists, and processes that need to allocate space in them must spend extra time scanning the long free lists while holding the shared pool latch. If your database is not yet on Oracle 9i database, an oversized shared pool can increase the contention for the shared pool latch. Shared pool latch. The shared pool latch is used to protect critical operations when allocating and freeing memory in the shared pool. Contentions for the shared pool and library cache latches are mainly due to intense hard parsing. A hard parse applies to new cursors and cursors that are aged out and must be re-executed. The cost of parsing a new SQL statement is expensive both in terms of CPU requirements and the number of times the library cache and shared pool latches may need to be acquired and released. Ways to reduce the shared pool latch are: avoid hard parses when possible, parse once, execute many. Eliminating literal SQL is also useful to avoid the shared pool latch. The size of the shared_pool and use of MTS, shared server option, also greatly influences the shared pool latch. The workaround is to set the initialization parameter cursor_sharing to force. This allows statements that differ in literal values but are otherwise identical to share a cursor, and therefore reduce latch contention, memory usage, and hard parse. Row cache objects latch. This latch comes into play when user processes are attempting to access the cached data dictionary values. It is not common to have contention in this latch, and the only way to reduce contention for this latch is by increasing the size of the shared pool, shared_pool_size. Use locally managed table spaces for your application objects, especially indexes. Review and amend your database logical design. A good example is to merge or decrease the number of indexes on tables with heavy inserts. Configuring the library cache to an acceptable size usually ensures that the data dictionary cache is also properly sized. So tuning library cache will tune row cache indirectly. DB CPU. This event represents the total time spent of the user's queries on the CPU. Oracle's background processes, SMON, PMON, are not included in this total time. If this value is high, it means that the Oracle instance spends most of the time on the CPU. To reduce this wait event, the SQLs in the SQL ordered by CPU section in the AWR report must be tuned. Log file sync. This event is known as the time lost as a result of the LGWR process waiting while users initiate a transaction commit or rollback. If this wait event is available continuously, I/O performance of the LGWR process is probably poor, or commit is coming too often by the application. The solution to this problem is not to commit too much, if necessary, and to examine the I/O performance of the disk on which the redo log files are located, and to use a high-performance disk such as an SSD disk if necessary. ENC, TX, row lock contention. Row lock contention. This type of event occurs when a user session is trying to update or delete a row held by another session, which is an application design problem.
Normally, when a transaction is finished, commit or rollback must be executed to release related rows. The solution to this problem is that if the session that holds the row is active, then execute commit statement. If it is not active, kill the session or execute rollback the session.
Arch wait on sendrec.
This wait event is the total time taken by the archiver processes to archive the standby in the data guard and to write these archives to the local disks. The main reason why this value is high is that the archives sent to the standby side arrive late due to the network. To solve this problem, it is necessary to optimize the network and set the default _SDU_size parameter in the sklnet.aura file to an optimized value, 32,767.
GC current block busy.
This wait event occurs between the nodes of the cluster database, real application cluster.
When a transaction requests a block, that request sent to the master instance. Normally, this request is performed by a cache fusion.
However, in some cases, this block transfer is delayed because the corresponding instance is held by the other instance or because the corresponding transaction records cannot be written to the redo logs immediately, in which case this wait event is triggered. This can be solved by tune the wait event log writer process or solving network problem between cluster nodes.
GC-CR block busy wait.
Difference is that while the above event is running in current mode, this wait event runs in CR mode. This can be solved by tune the wait event log writer process.